Welcome to Iron Process, where massive machines do not simply reach the end of their lives. They are dismantled, separated, refined, and reborn through systems of industrial precision. Have you ever wondered what truly happens to an aircraft after its final flight? When it leaves the sky for the last time, is that the end of its story? Or is it simply the beginning of another process that most people never get to see? Because an aircraft does not just disappear when it stops flying. It carries millions of parts, complex materials, advanced systems, and valuable engineering that can continue far beyond its original service life. The truth is simple: almost nothing on an aircraft is truly wasted. When an aircraft reaches the end of its operational life, it is not usually abandoned in a forgotten scrapyard. Instead, it is ferried to massive storage facilities, often located in dry desert regions such as Arizona or California. These locations are chosen because the hot, arid climate acts almost like a natural preservation system. Low humidity reduces corrosion, helps preserve the airframe, protects structural integrity, and slows the degradation of critical systems that would deteriorate much faster in wetter environments. Under these strict preservation conditions, the aircraft may wait for reactivation, resale, part out, or full disassembly. For many airlines and operators, this is not just a retirement zone. It is a strategic reserve where value can be extracted, extended, and redirected into new life cycles. Before any component is removed, the aircraft must first be made safe. This begins with one of the most critical baseline procedures in the entire process, the complete extraction of onboard fluids. Residual jet fuel stored inside the wings and fuselage must be drained using specialized industrial pumping systems, then transferred into sealed containment tanks for reuse or proper processing. This step is not simply about cleaning the aircraft. It is about eliminating risk. The operation is performed within a closed system where flow rate, pressure, and containment are continuously monitored to prevent leaks and reduce fire hazards. Even small traces of fuel can become dangerous under uncontrolled conditions, because one spark in the wrong environment can trigger a serious incident. After the fuel system is purged, technicians move to the hydraulic system. Although the aircraft is no longer flying, hydraulic lines can still retain significant pressure, and if that pressure is released suddenly, it can injure workers or damage equipment. Relief valves are opened in a controlled sequence to gradually dissipate pressure from the lines. Beyond fuel and hydraulics, other fluids such as lubricating oils, coolants, and specialized chemical agents are also collected separately. Each type of fluid follows its own protocol, because mixing them would create environmental and safety problems. Only after fuel is removed, pressure is neutralized, and hazardous fluids are eliminated can the aircraft be considered inert enough for safe disassembly. Once the aircraft has been rendered safe, the process enters one of its most economically important stages, the recovery of high-value components. At this point, the aircraft is no longer treated as a complete vehicle. It becomes an integrated system of separate technical assets, and each asset has to be assessed based on condition, certification, remaining service value, and market demand. Jet engines are usually removed first because they are among the most valuable parts on the entire aircraft. A single engine can be worth tens of millions of dollars, so it is never treated like scrap. It is carefully detached, inspected, evaluated, and either overhauled for return to service or repurposed for other industrial applications. Inside these engines are components such as turbine blades, which are manufactured from advanced superalloys capable of operating in environments exceeding 1,000 degrees Celsius. These blades must survive extreme heat, rotational stress, pressure changes, and continuous exposure to high-energy airflow, which makes them some of the most valuable parts to recover. At the same time, avionics systems, landing gear assemblies, control units, sensors, and other critical components are systematically removed, tested, and categorized. If they meet required standards, they can be recertified and reintroduced into the aftermarket aviation supply chain. This does not only maximize economic return, it also supports an industry where new manufacturing is expensive, lead times are long, and every certified component carries significant value. After the most valuable systems have been recovered, the remaining aircraft enters full-scale disassembly. The focus now shifts from recovering individual high-value assets to breaking the aircraft down into independently processable sections. Inside the passenger cabin, every element is removed and sorted. Seats, overhead bins, interior panels, wiring systems, insulation, flooring, lighting units, and other cabin components. Some of these parts can be reused or repurposed in other industries, while others are directed into specialized processing streams. Even components that look simple, such as wheels, tires, and landing gear parts, are the result of intense engineering. Aircraft tires, for example, are not ordinary rubber. They are reinforced with high-strength aramid fibers and inflated with dry nitrogen to reduce the risk of fire or explosion under extreme heat and pressure. The carbon brake systems connected to the landing gear are engineered to absorb enormous amounts of energy during landing, rapidly converting kinetic energy into heat. Every component removed from the aircraft must also be accompanied by detailed technical records and traceable certification. This documentation is essential because aviation does not allow uncertainty. If a part is to re-enter the supply chain, its history, condition, and compliance status must be clear. Without that record, the part may have material value, but it loses aviation value. As all internal systems are stripped away, the fuselage gradually emerges as a bare metal structure. At this point, specialized cutting equipment begins segmenting the fuselage and wings into large sections, preparing them for the next phase of material processing, where the aircraft no longer exists as a complete form, but transitions into an entirely different state. Once the interior and major systems are stripped away, the remaining aircraft structure moves into large-scale mechanical processing. The fuselage, wings, and major structural sections are cut into smaller segments before being shredded into uniform metal fragments. This is the point where the aircraft fully transitions from a recognizable machine into raw, reprocessable material. These fragments pass through automated sorting systems designed to separate aluminum, titanium, steel, and other alloys. Magnetic fields, eddy current separators, and advanced material sensors are used to identify and divide different metal groups. This separation is critical because recycling efficiency depends on purity. If different alloys are mixed incorrectly, the final output loses quality and may no longer meet technical standards for advanced manufacturing. Once sorted, each metal group is fed into specialized furnaces for melting and refining. During this phase, impurities are removed and chemical compositions are carefully controlled so the material can be restored to a consistent state. Recovery rates can reach approximately 85% of the aircraft's total weight, meaning most of the original structure is not lost. It is transformed into new raw material and prepared to re-enter industrial production in a completely different form. After melting and refining, the recycled metal enters the forming stage. The molten stream is fed into a continuous casting system where it flows through water-cooled molds. As the metal contacts the mold walls, the outer layer rapidly solidifies, forming a stable shell around a still molten core. Under tightly controlled temperature and withdrawal speeds, the material is gradually shaped into long, semi-finished products, such as billets or slabs. These forms are not the final product. They are intermediate feedstock for the next stage of industrial processing. Because they still retain extremely high temperatures after casting, they can be transferred directly to the hot rolling line. There, the metal passes through a series of rotating rollers that compress and elongate it in multiple stages. With each pass, the material becomes thinner and longer until it reaches the required dimensions. The elevated temperature preserves ductility, allowing the metal to deform evenly without cracking. Throughout the process, sensors monitor thickness, temperature, and rolling speed to ensure the final product meets strict technical specifications. At the end of the line, the recycled alloy is formed into uniform sheets or coils, ready for future manufacturing across multiple industries, including aerospace. Even after casting and rolling, the material still has to be stabilized. It exits the production line at extremely high temperatures and is cooled through a controlled process using high-pressure water sprays. This allows heat to dissipate evenly while stabilizing the internal structure and reducing the risk of distortion or cracking. Once the temperature normalizes, the material enters quality assurance. Representative samples are tested to verify chemical composition, while mechanical testing evaluates strength, hardness, durability, and load-bearing performance. Every parameter must meet engineering standards before the material is approved for use. If the material passes inspection, it is cut into standardized dimensions, labeled, documented, and moved into storage systems. Each batch must remain traceable throughout the production chain, because industrial recycling at this level is not just about melting scrap. It is about turning recovered material into reliable input for future manufacturing. From there, the recycled metal can become part of industrial equipment, advanced technologies, high-performance engineering applications, and even new aerospace components. At this point, the original aircraft no longer exists as a complete machine, but its value continues to move through new systems, new forms, and new life cycles. This raises a deeper question. Is this recycling logic truly applied because of environmental responsibility, or only because it produces economic value? In reality, many large-scale environmental initiatives become practical when financial incentives exist. Aircraft recycling works because the materials are valuable, the components are expensive, and the aviation supply chain depends on certified parts. So is this a long-term sustainability commitment, or simply an optimized equation of profit? The answer may depend on perspective, but the process itself reveals one thing clearly. When engineering value is high enough, the end of a machine becomes relative. If engines are the heart of an aircraft, then tires are its legs. Consider the Airbus A380, an aircraft weighing more than 500 tons at takeoff, supported by only 22 tires. During landing, those tires go from complete stillness to hundreds of kilometers per hour almost instantly, while carrying immense loads and enduring extreme friction. With every touchdown, a single tire can withstand loads of tens of tons, comparable to multiple cars pressing down on one small contact point. And this cycle is repeated hundreds of times over the lifespan of a single tire. What prevents failure is not luck. It is advanced material engineering. Aircraft tires are multi-layered composite structures reinforced with aramid fibers, a class of high-strength materials also used in ballistic protection. These reinforced layers are embedded and stacked to create a framework capable of holding shape while absorbing violent impact forces. Additional internal reinforcements limit deformation under high-speed rotation and heavy loading. The tread pattern is also designed with purpose. It is simpler than a car tire, often using straight grooves to evacuate water quickly and reduce the risk of hydroplaning during wet runway landings. The manufacturing process for aircraft tires is equally controlled. The tire is placed into a mold and cured under high temperature and pressure, bonding all layers into one unified structure with the strength and elasticity required for extreme operating conditions. But manufacturing alone is not enough. Before entering service, each tire must undergo rigorous testing, including pressure resistance tests, high-speed acceleration tests, and landing simulations under real-world conditions. And one of the most surprising details is that aircraft tires are not always single-use items. In many cases, the internal structure can be reused through retreading, where the worn outer rubber is removed and replaced with a new tread layer. This allows a single tire structure to support hundreds of takeoff and landing cycles before final retirement. Behind their simple appearance, aircraft tires are highly engineered systems built to perform under extreme stress while maintaining one critical outcome: safety at every touchdown. The entire process of aircraft disassembly and recycling reveals a fundamental truth. The value of a machine does not end when it stops operating. It depends on how effectively that machine can be repurposed after its primary life cycle is over. An aircraft may no longer fly, but it does not become obsolete. It is systematically deconstructed into engines, avionics, landing gear, structural aluminum, titanium alloys, reusable components, and recyclable materials. Each element is inspected, evaluated, and classified to determine whether it can return to service or be transformed into raw material. Components that meet operational standards re-enter the aftermarket supply chain, while remaining materials move through mechanical processing and metallurgical refinement to become new industrial inputs. With recovery rates reaching up to 85 to 90% of total mass, most of the aircraft is not discarded. It is reintegrated into production in more suitable forms, from industrial materials to high-performance engineering applications. From a technical standpoint, this system is designed to minimize waste, preserve material value, and extend life cycles. Some components are reused directly, while others are broken down and transformed into feedstock for entirely new production cycles. Value is not lost. It is restructured into forms that better align with future use. In this context, the idea of an end becomes relative. An aircraft does not truly disappear when it stops flying. It simply stops existing in its original form, while its parts, materials, and engineering value continue across new systems and applications. And perhaps the most interesting paradox is that some of the least visible components are the ones exposed to the most extreme conditions. So if you had to choose one aircraft component that impresses you the most, the engines, the landing gear, the tires, the avionics, or the structural materials, which one would it be? Thanks for staying with Iron Process. If you enjoy seeing how massive machines are dismantled, processed, and reborn, stay connected, because every industrial ending is only the beginning of another process.